Okay, let's continue to the contents of section 6.4, line with reactive load and discontinuities. So in this slide, we see the transmission line circuit, which is terminated with an inductive load. That is, the right end of the transmission line circuit is connected to an inductor. So we would like to see what happens in this circuit. And this transmission line circuit begins with zero initial currents and no voltage on the line. So as the switch closes on at t equal to 0, then the source, now that this is a DC source, a battery, the source will provide a V plus signal that goes from left to right in the transmission line. The amount of V plus signal is what? Using the voltage division law, that should be half of V sub 0 because the inner resistance of the generator is Z sub 0 and the characteristic impedance of the transmission line is Z sub 0 as well. So the V plus signal we have, the initial signal will be half of V sub 0. And because of the characteristic impedance of the line is Z sub 0, then the I plus signal, the current, goes toward the positive Z direction, goes to the right, is V sub 0 over 2 times Z sub 0. All right? So the initial V plus and I plus signal is not that difficult to find. And at a certain times later, that is, the propagation delay for the signal goes on the line until it reaches the right end, which is located at Z equal to L. Z equal to L. And because the line is terminated with an inductor, the original V plus I plus signal, the ratio of the V plus I plus signal is not consistent, is not compatible with the voltage and current relationship on the inductor. Therefore, we shall have the V minus and I minus signal due to the discontinuity at the right-hand side. And knowing that the V minus I minus signal also abide the characteristic impedance relationship, that is, V minus is I minus equals to the minus of V minus over Z sub 0. So we can find the total current, the total voltage. The total voltage here is V sub 0 over 2 plus V minus. And the total current is here. So far, we still do not know the exact solution for V minus signal, right? But we can use the boundary condition, that is, the voltage and current relationship on the inductor, to help us to find the expression for the V minus and the I minus signal. So the key is the relationship of voltage and current on an inductor. So refers to the equation to the left, we see for an inductor, the voltage across the inductor must equal to the inductance times the time derivative of the currents in the inductor. So that will be dIL over dt times L equals to V sub L. So we substitute the total voltage over here as VL voltage the currents IL can be replaced. I'm sorry. So this is the voltage. This is the current. So the IL current is substituted into this small parenthesis. So what is the next thing? The next thing is to performing the differentiation of this parameter. So what is the result of taking the time derivative of this expression? Well, the first term, which is made of all constants, should goes to 0, right? It has no time dependence. The V minus signal, as a result, should be a time-dependent function. So we know that the first thing goes away. The second thing, V minus must, the Z sub 0 can be taken out of the differentiation operation, but we need to preserve this time derivative expression over here. So equation 6.52 is a first order partial differential equation. It has the first derivative of V minus signal and these things. Well, that's the V minus signal without taking any derivative. So this is the first order derivative. This is the zeroth order, and to the right is a constant. Okay, and because we can identify this as a first order differential equation, we can find out the general solution for this kind of first order partial differential equation. And here we need to, so what is the general form? Well, it's in here, 6.54. So it's an exponential function. This kind of function can satisfy the first order partial differential equation, providing that we can calculate the other parameters of this function. For example, you need to satisfy the initial condition. So let's read the first sentence over here. The initial condition is that the current through the inductor is 0 at t equal to capital T. What is capital T? Capital T is the time required for the signal to propagate from the left-hand side to the right-hand side. Because the circuit is, the switch is closed at t equal to 0. And then with some time delay, that is the capital T in this case, the signal, the V plus I plus signal will reach the right-hand side of the microwave circuit. Okay, so that will be the initial time for the inductor to do what? To charge up. So what we do is charging up the inductor. As you know, with no energy stored in the inductor acts as a short circuit. On the other hand, when the inductor is fully charged, it becomes an, I'm sorry, at the beginning, without any charging, it becomes, it's an open circuit. After you charge up the inductor, it becomes a short circuit. Okay, so it's just the opposite of a capacitor. So it starts as an open circuit. Then once you fully charge it, the impedance goes to 0, so it's equivalent to a short circuit. All right, so at t equal to capital T, the inductor behaves like an open circuit. So what happens if you have an open circuit termination? Then the V minus signal will of the same magnitude of V plus signal, and they will be in the same sign. 就大小相同，然后也是同样的极性，哈，所以你看到 6.53 的红框框 V 负讯号在 t 等于大 T 的时候，它的 V 负讯号的大小是0/2V0，然后呢，极性呢是正的，所以跟 V 正讯号是一样的。OK， 好，为什么？因为在 T 等于大 T 的这个当下，这个 moment， 你的电感元件可以被视为是一个开路啊，所以我们还是偷偷的利用开路的那个反射系数，也是伽马等于1的这一个关系，找出了 V 负讯号的初始电压。不过要注意哦，这只是初始电压 ，V 负讯号会是一个时间的函数，所以随着时间推演，它的电压值不会一直都是0/2V0啊，而会是一些其他的数字啊，其他的数字。OK， 那在求解这个问题的时候，有一个东西要先找出来的，叫做时间常数 （time constant） 啊。So for this kind, for inductors, I bet that as when you have your circuit theory classes, you know that for inductors and capacitors to find out its voltage current relationship, you need to find out the time constant for the inductor and capacitor. So what are the formulation? What are the formulas for inductor and capacitor's time constant? So let's check out which result. Shoot. Over here, okay? So the time constant for inductor is L/R. And the time constant for capacitor is RC. Okay? But be careful here, what is R? That should be the impedance viewed by the capacitor and the impedance viewed by the inductor. 也就是电容看到的等效电阻，或者是电感所看到的等效电阻，是这里所写的 R。好，所以要小心的一点是，这个 R 是电感跟电容所看到的等效电阻，而知道它的等效电阻，再加上电感电容本身，就可以得到它们的时间常数啊，时间常数。So yeah. So it's actually the general solution for this kind of first order partial differential equation. The general solution is in the form of a constant A times exponential minus T over tau. Okay, in this form. Tau is the time constant. But here, T should be replaced with T minus capital T. Why? Because for the inductor, everything starts at the instant of T equal to capital T. And the time constant can be substituted as Z sub 0 over L. Because tau equal to L over Z sub 0. Okay, why? because for the inductive termination, the impedance mu from the inductor is what? Is Z sub 0 to the Z sub 0 on the left. Okay, so for this case, the impedance mu by the inductor is simply Z sub 0. Okay. However, if the inductor or the capacitor is placed in the middle of transmission line circuit, things may get a little bit complicated, as we will see a few questions in the Zoovio test today. 不过啦，我会先给你做一点点练习啦，好。All right, so what? Okay, so once you find the initial voltage of V minus, we can write up this kind of relationship. The general solution for the differential equation can be written in this form, and we still don't know the constant A, which requires to be solved with initial condition. So let's move on to the next page. Okay, and we know that at t equal to capital T, this V minus should be just V sub 0 over 2. Okay, so we evaluate the general solution by substituting the initial condition. That is, T equals to capital T, and V minus equals to V sub 0 over 2. Okay, so we replace V minus and lowercase t with the initial condition like this. So it turns out the constant A can be expressed as V sub 0 times exponential Z sub 0 over L times capital T. And so the next thing is we can substitute the original general solution with the known A value, and it becomes equation 6.56. Not that this solution is only valid for T is greater than capital T. When T is smaller than capital T, what is the V minus signal? Just 0. All right? Now, so 6.56, the question, the equation in the middle is the solution for the V minus voltage signal. And for the current, you simply divided the V minus signal with Z sub 0 and a minus sign will be your current solution. So as you can see, they are all time functions. They are time dependent function. And because the V minus signal is the time dependent function, so the concept of reflection coefficient, as we mentioned in the last week, which is defined in terms of V minus over V plus, is not applicable for transient behavior for inductive or capacitive termination. So for reactive load, and if you perform transient analysis, the concept of reflection coefficient is not applicable for those kind of problems. All right. So we know that because of the inductive termination, it will set up a V minus and I minus signal going to the left. And they are all time-dependent function. So what happens when they travel back to the source? What happens? Well, nothing happens because on the left-hand side, the battery comes with an inner resistance of Z sub 0, which equals to the characteristic impedance of the transmission line. So because of this matched impedance condition, they will set up no further reflections. Okay? So we don't have to calculate the V minus plus signal as we have done before, because there is no further reflection on the left-hand side. So what happens once we close up the switch? Once we close up the switch of the transmission line circuit, the battery will start to charging up the inductor. So at the beginning, the right-hand side should act as an open circuit, right? Because the inductor is not connected at the beginning. Once it is fully charged, it becomes a short circuit. So what is the steady state? What is the steady state voltage and current at this point? Steady state current and voltage. Well, the VSS steady state voltage at Z equal to L, the right hand side should be what? 0, because it's a short circuit. ISS should be what? V sub 0 over 应该这样吧？对啊，因为当你到 steady state 的时候，传输线本身没有嘛，然后右端又变成什么短路，所以你的总电流应该只剩下 V0 除上 Z0。好 ，All right. So what else? Okay. So at this point, it can be seen that, unlike in the case of linear resistive termination and discontinuity, the concept of the reflection coefficient is not useful. It's not applicable for the study of transient behavior when reactive elements are involved. So for time domain transient analysis, you cannot apply the concept of reflection coefficient on reactive elements. However, in chapter 7, when we perform frequency domain analysis, the concept of reflection coefficient is still applicable for reactive components, because in that case, we are talking about steady state characteristics of the transmission line, which is not the same case as we have here. And the reason why concept of reflection coefficient is not acceptable, is not applicable for time domain analysis, is because either the current or the voltage, both the current and voltage are time-dependent functions, which are not constant, as the reflection coefficients suggest. So we may now write the expression for the total voltage across the inductor and total current through the inductor. Because what we have just derived is the V minus. The reverse going voltage signal, not the total voltage signal on the inductor. But it is not that difficult. For the total voltage on the inductor, that will be the sum of the V plus and the V minus signal. So we just add up the two. So use the expression we derived in the previous slide. The sum, the addition of V minus and the V plus signal will be simply this. V sub 0 times the exponential of minus Z sub 0 over T times T minus capital T, okay? And 6.59 is the total current. That would be the sum of I plus and I minus signal. So as you can see here, it's just V0 over Z sub 0 times this. So they should be complies with this relationship. If you substitute 6.59 and 6.58 here. And okay, so the interesting part is drawing the voltage and current variation on the time domain. So you must learn how to draw this kind of plots, because I enjoy having this kind of questions in your midterm. 我特别喜欢看图啦，好不好？那看图也改起来也方便嘛，一看就知道，一翻两瞪眼，所以图要画得清楚像这种 reactive load 的这种的话，它那个电压变化、电流变化就不是线性的，就不是线性的，它是 exponential function 嘛，不过这边我们看到一些，像等一下6之5的一个 example， 你会看到线性的图形啊，反正期中考一定会碰到作图啦，所以要记得带尺啊，应该不用带圆规了，不用要带尺啦，要记得带尺。Okay, so the top right is the voltage is the time domain voltage variation on the inductor. So before capital T, there's nothing appear in the inductor. So the voltage is 0. And when the V plus signal arrives, which is V sub 0 over 2, it set up a reflecting signal of V minus, which is V sub 0 over 2 as well, at the t equals to capital T. So the sum of the V plus and V minus signal shall be V sub 0. V sub 0. And if you interpretate it in terms of the behavior of the inductor component, because it acts like an open circuit, so the total voltage, the V plus and V minus signal appear on the inductor will be V sub 0 in this case. Then, as you know, the battery on the left-hand side will charging up the inductor on the right-hand side. So eventually, the inductor becomes a short circuit. So as you can foresee, the total voltage across the inductor will becomes 0 eventually, or becomes 0 in the steady state. So as you can see from the horizontal axis, as time enlarges, the voltage across the inductor shall approaches to 0. To fully complete this figure, complete this plot, you need to draw the characteristics of the so-called time constant. As we already calculated, the time constant for this inductor-terminated transmission line is L over Z sub 0. So what is the significance of time constant? Which means the signal, the voltage signal or the current signal, the magnitude becomes exponential minus 1. Right? At the time constant, one time constant, the exponential part will become exponential minus 1, which equals to what? 0.36a. Am I correct? I'm supposed to, yeah. 所以在一个 time constant 的时候，它的那个讯号大小会下降到原本的36%、37%嘛，所以除了把那条线画成那个，这叫 concave up， 朝上的弧线，concave up， 然后你要注意那一个位置，voltage 的那个大小位置是 V0 V sub 0 times exponential minus 1, which is about 1/3 of the initial voltage at the position of one time constant. All right, and you can do the same for the total current. So prior to the time instant of capital T, the total current appears on the inductance is 0, and it is 0 at t equals to capital T because it acts as an open circuit. But it will eventually charge up and appear as a short circuit. Then the total currents appear on the inductor will be V sub 0 over Z sub 0. And you need to mark the position of one time constant and show the correct current level to get full credit from the meter exam. OK? 所以要练习啦 ，homework 里头的类似题要练习，课本上的 example 要练习，好不好 ？So it can be seen from the sketches that in the steady state, which is t approaches to infinity, the voltage shall go 0 and the current becomes V sub 0 over Z sub 0. This is consistent with the factor that the inductor behaves like a short circuit for DC voltage source in the steady state. Okay. All right. So let's check up another example. This example is a little bit interesting because the reactive load is placed as a discontinuity. So example 6.5 is the case of a capacitive discontinuity. So it plays in the middle of the transmission line. And the value of the capacitor is 10 picofarad. So what is the first thing we need to find here is time constant. Okay? So for the capacitor, what is the time constant? Okay, let me rephrase my question. What is the impedance viewed by the capacitor? So the capacitor, if you are in the capacitor, you look to the right, you see what? You see Z sub 02, which is 150 ohm. If you look to the left, you see Z sub 01, which is 50 ohm, right? So what is the total resistance you see in the 10 picofarad capacitor? 200, because the one is in the front, the other is to the other end, so it's kind of a series connection. 串联嘛，所以 50 ohm in series with 150 ends up as an equivalent resistance of 200. So the time constant, that is resistance times the capacitance, will be 10 pico times 200. That will be 2 times 10 to the minus 9, 2 nano, okay? So 2 nanoseconds is the time constant for this case. All right. So what happens if the capacitor appears as a shunt capacitor, not a series capacitor, a shunt capacitor? What is the equivalent resistance viewed by the shunt capacitor? That would be 50 in shunt with 150. So that would be what? 50变150多少？537.5 ，OK 哈 ，OK 好，不错，至少大家算数没问题哈 ，OK 哈。会啦哈，所以你假如是串联的话，那个数字变小嘛，对不对？变联的话数字变小嘛，串联数字变大嘛，So that would be the same thing if in the middle is an inductor, right? But the equation that you need to calculate it's the same. You use the same principle to find the equivalent resistance viewed by the inductor, but the time constant expression is a little bit different for capacitor and inductor. 有了，这个以前考古题有出过这个类似题啊，当然你可以比较有把握的是，我大概不会再开串联电容了，可能是串联电感啊、并联电感啊、并联电容之类的，很难讲啦，难讲。你先看考古题啊，考古题看它是串联还是并联的，我大概比较不会。其实你可以慢慢猜出规律啦，就是有些题目你就知道老师一定会出的，但老师绝对不会出跟那个考古题上面一样的嘛，起码要动一点数字嘛，对不对？表示我对各位的尊重，对不对？所以当然考古题本身要会啊，不是把答案背下来，是把方法背下来，好不好？然后再 apply 到那个，OK。好，我也不是要给各位找麻烦嘛，我们转一个弯就好了，我们要转3、4个弯嘛，对不对？Okay, so what happened with the result? Okay, so as you can see, the propagation delay for the first section is 1 nanosecond. How about the second section? Oh, well, we don't have to worry about the second section because what? Because why? Because the right-hand side is terminated with another 150 ohm, which will set up no reflection on the right-hand side. Okay, so we will only view the V plus signal. So when you look at the plots like this, you need to be careful about the horizontal axis and vertical axis. Okay, so in this case, the horizontal axis is the time marks, okay? So from 0 nanosecond to 2 nanosecond, 4 nanoseconds. So this is a plot view in the time domain. The vertical axis shows the voltage. The voltage of what? The voltage for Z equal to 0. So that would be the voltage on the left-hand side of the transmission line. Okay, sometimes I may ask what the voltage in the middle of the line or at the right-hand side of the line. Okay, so you need to be careful about the position of the voltage and currents that we are interested. Okay, so here we are looking at the voltage on the left-hand side. So at the beginning, the initial voltage will be 10 volts, which can be calculated easily with this voltage diffusion law. So that would be 10 volts. And why is set up? Why this thing becomes 15? Why? Well, the complete solution is on the textbook, okay? But you should check out why the well, as you can see here, the V minus signal is 5 volts. The reverse going voltage set up by this capacitive discontinuity will be 5 volts. And as the time progresses, the capacitor shall become a short circuit or an open circuit. So eventually, the transmission line will be broken up in the middle. So the total voltage on the left-hand side will approaches to 20 volts. Okay, because the middle becomes an open circuit, so the transmission line is broken up. And in the steady state, the effect of the transmission line shall plays no role in this circuit. So you just have the 20 volt battery on the left hand side. And you can see that the voltage climbs up gradually. So why we mark 18.16 here? Because 4 microseconds is what? The time constant of the capacitor. The time constant of the capacitor, as we calculated earlier, is 2 nanoseconds. Okay, so the voltage will go from 5 to 8.16, and eventually the voltage will becomes 20. Okay. All right. Yeah, I guess we can start. We can start tomorrow. We can start section 6.5 tomorrow. Okay. So, all right, let's stop here. Okay. 好吧，所以呢。